Hello everyone. Uh, Today we'll start with factors affecting adsorption of gases on solids. The first factor is nature of adsorbate. Adsorbate is the one who is coming to the surface of adsorbent to get adsorbed. Now there are two types of adsorption, chemical adsorption and physical adsorption. Now in case of chemical adsorption, it is highly specific and only those gases are allowed to adsorb on a specific solid which can form chemical bonds with it. So this is the nature of gas adsorbate, which allow it to either bond with the adsorbent or not to bond with the adsorbent. But in case of physical adsorption, there is no specificity in nature. Therefore, every gas gets adsorbed on any solid surface, but it depends which adsorbed lesser or which adsorbed greater. Now, the easily liquefiable gases which have low critical temperature can adsorb easily. High critical temperature can adsorb easily, which can be liquefied easily. They can adsorb easily than the other ones. So this is the dependence on nature. Like the first factor is the one who can the gases who can get chemically bonded to the adsorbent. They can adsorb chemically, and those who are easily liquefiable adsorbed greater than the others who cannot liquefy easily in case of physically adsorption. Now the second factor is adsorbent. Now the general adsorbents, the common adsorbents are activated carbon, powdered carbon, metal oxides like aluminium oxides, silica gel, and clay are the common adsorbents. So the adsorption depends on the pores, on the imbalanced forces on their surfaces, right? So it is the surface which decides the extent of absorption also. Now, surface area, surface area, surface area of adsorbent. The gases can be adsorbed more if more exposed to the adsorbent. So if adsorbent gives more exposure, it means it is finely divided. It means its surface area is large. Then the gases can be adsorbed easily. The pores on the surfaces should be large to enter the molecules, imbalanced forces. Next is pressure. Now the pressure physical adsorption increases with increase in pressure. Physical adsorption is non-specific and it depends only on the contact of adsorbate and adsorbent. So the gases on giving pressure comes closer to the surface of the adsorbent and the adsorption increases. Uh, uh, this the factor of pressure, the effect of pressure is studied by adsorption isotherms, and adsorption isotherms are the graphs, the curves, which shows the variation in the amount of gas adsorbed on the adsorbent by taking the temperature constant with pressure. By change in pressure, the amount of gas adsorbed on the adsorbent with pressure, it is the graph in between the amount of gas adsorbed on the adsorbent and pressure by taking the temperature constant. And the adsorption isotherm, which is in our syllabus, is Freundlich adsorption isotherm, and it is the relation between x upon m and pressure. Now, x is the mass of gas adsorbed on per unit mass of solid. X is the mass of gas, and m is the mass of adsorbent. And the equation is x upon m is equal to k p raised to power 1 minus n, and the value of n and k depends on the nature of gas, nature of adsorbate, right? Now, the next is the graph between x and m, and the graph shows at the low temperatures the variation of x and m is uh, here at low pressure the x upon m varies directly proportional. X upon m is directly proportional to pressure. So as the pressure increases, the adsorption increases. Whereas in case of very high uh, uh, pressure, the dependence of this uh, pressure, the dependence of adsorption on pressure will no more work. There is no dependence on pressure of adsorption. So here the graph is flattened, and with the increase in pressure, the adsorption is no more increasing, right? Now, in case of moderate pressure, the relation this x upon m is equal to p raised to power 1 upon n works, and on applying logarithm to both sides, we get this graph, and here um, the slope in if we are drawing graph in between log x upon m and log pressure, this slope represents the value of 1 upon n. Next is catalyst. Now, catalysts are the substances which alter the rate of a chemical reaction, which can alter, which can increase or decrease. Generally, they increases the rate of reaction. And in this process, they themselves remain chemically quantitatively unchanged, chemically and quantitatively. They are not going to consume in the reaction. So these are the catalysts. The promoters are the substances which comes along with the catalyst and enhances the activity of catalyst. Like molybdenum comes along with iron as catalyst. Iron as catalyst and molybdenum as promoter in case of Haber's process, where nitrogen and hydrogen combines to form ammonia gas. So molybdenum acts as promoter here. So promoters are the substances which enhances the activity of the catalyst, and catalysts are the substances which alter the rate of a chemical reaction by not consuming themselves in the chemical reaction. Now, next is the catalytic poisons. Catalytic poisons are the substances which decreases the activity of the catalyst. They are opposite to the promoters. So arsenic is a substance which decreases the working of vanadium pentoxide, which is working as a catalyst in contact process of production of sulfuric acid. Now, next is types of catalysis. So there are two types of catalysis. The one is homogeneous catalysis, other one is heterogeneous catalysis. Homogeneous catalysis means the catalysts are the same physical state as the reactants are. So if reactants are liquids, so catalysts are liquid. If reactants are gases, catalyst is also gases. But heterogeneous catalysis is mainly for gases as reactants and solid catalysis. So they are not in same phase. They are not in same phase. Next topic is activity of catalyst. Activity means the ability of catalyst to increase the rate of reaction, and this ability depends on the nature of catalyst, on the nature of bonds of catalysts with the reactants. They should not be so strong that the product cannot be released. So if the product cannot be released from the surface of catalyst, it means the activity of catalyst will decreases with time. So the bonds of catalyst should be so strong that a chemical reaction can take place, but it should not be so strong that the sides of the catalyst will remain permanently blocked. So this is the activity of catalyst. Its ability to catalyze the reaction, to increase the rate of the reaction. Next is the selectivity of the catalyst. Next topic is selectivity of a catalyst. Selectivity means ability to produce desired product. So catalyst decide the product from the same reactant. So here is an example: carbon monoxide and hydrogen. So carbon monoxide and hydrogen, in case of nickel solid catalyst, produces ammonia. Methane, produces methane, and in case of copper, zinc oxide, and chromium 6 oxide, they produces methanol, and in case of copper solid catalyst, they form formaldehyde. So same reactants, same reactants gives different types of products with different catalysts. So it is the catalyst who decides the desired product. Now, mechanism of adsorption theory of heterogeneous catalysis. So this theory is very simple. So the catalysts have imbalanced forces on their surfaces. They have imbalanced forces on their surfaces. Like the molecule in the interior have same forces from all around, uh, from the molecules all around it. But the molecule present, but the atom present at the surface have imbalanced forces. So to balance the forces, they can attract the external particles. So the reactants molecules diffuses to the surface of the catalyst. After diffusion, they get adsorbed. They get adsorbed. Like here, the reactants A and B are adsorbed. Now, when they get adsorbed, then reaction will be carried out at the surface of the catalyst and intermediate species is formed. This is intermediate species. This is intermediate species. So this theory produces intermediate species with the catalyst. Reactant and catalyst produces intermediate species. Then when the intermediate species form, then product dissolved from the catalyst. Product detached from the catalyst. Then after desorption of the product molecule, the product molecules diffuses away from the surface of the catalyst and making available the surface for the next molecules. So in whole whole of this process, the catalyst become quantitatively and chemically same. It will become same as in the original state. So reactant comes, they adsorb, intermediate form, product, the reactant changes to product, products detach from the surface, they diffuse away from the surface, and catalyst uh, again ready for the next reactant molecules to uh, react. Shape selective catalyst. So these are the catalysts which depends on the pore size, pore structure of the catalyst, and the molecular size of the reactant and the product. So they are the two factors on which this works. One is the pore size on the surface of the catalyst, and the second is the size of reactant and product molecules. Now, example is zeolites are the shape selective catalysts. They are also known as microporous aluminosilicates, right? So they works on the principle of their pore size and the size of reactant molecules and products. Only those reactants are allowed to react on their surface which can fit exactly in their pores. So in case of zeolites, they have aluminium, oxygen, silicon, three-dimensional network, and in this network they have honeycomb-like pores. So only those reactants which can fit in these pores are allowed to react, right? So these are known as shape selective catalysts. So ZMS5 is an example which converts the alcohol to gas. ZSM5 is a zeolite which converts alcohol to petrol by dehydrating them to give a mixture of hydrocarbons. So thank you. This is all for now. So we'll do the next topic tomorrow. Thank you.